Every second, 40 kilograms of water vapor stream away from an interstellar comet, vanishing into the void of space in a region so distant that our own comets remain frozen and silent. In July 2024, NASA's Swift satellite observed something unprecedented. This comet, designated 3IR Atlas, was ejecting steam like a cosmic fire hose at a distance of 2.9 astronomical units from the Sun, an intensity of activity never before witnessed in a visitor from beyond our solar system. But the puzzle deepens with every observation. If 3IR Atlas is hemorrhaging water at such an alarming rate, why does its surrounding cloud, the coma, teem with strange icy fragments? And why did the James Webb Space Telescope detect carbon dioxide dominating over water by a ratio of 8-to-1 just days after the Swift observations? This isn't merely another comet passing through our neighborhood. It's a cosmic enigma that defies explanation, and unraveling it could fundamentally alter our understanding of what exists in the vast spaces between the stars. So what secrets is 3IR Atlas concealing? In late July 2024, NASA's Swift Observatory directed its ultraviolet instruments toward 3IR Atlas, searching for the telltale chemical signatures that reveal a comet's activity. The spacecraft's ultraviolet and optical telescope, positioned high above Earth's obscuring atmosphere, detected an unmistakable signal: hydroxyl radicals, fragments of water molecules, glowing in the frigid vacuum, their presence betraying the destruction of water vapor by solar radiation. Over the course of a week of accumulated observations, the Swift team calculated that the comet was shedding water at a staggering rate of nearly 40 kilograms every second. This wasn't a gentle trickle but a deluge, a flow rate comparable to a city fire hydrant, erupting from an object situated almost 3 times farther from the Sun than Earth orbits. At 2.9 astronomical units, most comets native to our solar system remain dormant, their ice is imprisoned by the bitter cold. Atlas, in stark contrast, was hurling water into space with reckless abandon. The magnitude of this activity immediately raised profound questions. Mathematical calculations reveal that to sustain the observed water production, at least 8% of the comet's surface would need to be actively sublimating, converting directly from ice to vapor. This percentage far exceeded the 3 to 5% typically observed in local comets at comparable distances. For a nucleus estimated to measure between 5 and 6 kilometers in diameter, this translated to more than 7 square kilometers of exposed, sunlit ice actively venting into space. Yet the ultraviolet emission wasn't concentrated tightly around the nucleus as expected. Instead, it spread across an extended, diffuse cloud, suggesting an additional source of water vapor. Sophisticated models pointed to a swarm of icy grains, tiny fragments, each functioning as a miniature steam vent. As sunlight struck these grains, it could vaporize water across vast distances, amplifying the apparent activity far beyond what the nucleus alone could generate. Near-infrared observations from the Gemini Observatory and the Infrared Telescope Facility confirmed the presence of water ice in the coma itself, not just on the central core. The Swift team's Hazer modeling technique, which translates hydroxyl emission into water production rates, accounted for this extended source, but the resulting numbers still push against the boundaries of what conventional comet physics could explain. Every measurement underwent rigorous scrutiny. Calibration procedures, background subtraction techniques, and sensitivity thresholds were debated extensively in team meetings, yet the signal remained consistent and undeniable. The extended hydroxyl emission, the exceptionally high active fraction, the grain-driven outgassing, all converged on a single, inescapable conclusion. 3IR Atlas was venting water at a rate and in a manner never before documented in an interstellar visitor. The question had evolved from whether the activity was genuine to what hidden mechanism, buried deep within the coma or nucleus, could sustain such a spectacular display so far from the sun's warmth. August 6 introduced a new dimension of complexity to the 3IR Atlas enigma. The James Webb Space Telescope, employing its Miri and NIR spec instruments, captured spectra that unveiled a chemical composition almost unprecedented among known comets. Carbon dioxide was dominating water by a ratio of nearly 8-to-1. This wasn't a subtle variation. In the vast majority of comets, water reigns supreme as a primary volatile component. Carbon dioxide typically plays a supporting role, never seizing center stage. But hey, the ratio stood at 7.6 to 8. For every single molecule of water, there were nearly 8 molecules of carbon dioxide. This value deviated several standard deviations from the norm established by both long-period comets and Jupiter family comets. The JWST team, led by expert planetary spectroscopists, meticulously mapped the coma in infrared wavelengths. Their data revealed more than mere numerical ratios. Water vapor, the traditional driver of comet activity, manifested in scattered, patchy bursts, appearing localized and uneven, almost as if it were leaking from isolated vents or erupting sporadically from individual icy grains. By contrast, carbon dioxide painted a broader, more uniform distribution across the coma, suggesting a fundamentally different release mechanism. This contrast between patchy water and smooth carbon dioxide distribution indicates that the two volatile compounds are being liberated through inherently different processes, or perhaps from distinct reservoirs within the nucleus and its surrounding debris field. Other molecular species enrich the chemical portrait. Carbon monoxide was detected, adding to the carbon-rich profile. The team also identified traces of carbonyl sulfide, a sulfur-bearing molecule rarely observed in such abundance in comets. Each of these compounds carries vital clues about the comet's formation history. The high carbon dioxide abundance could indicate formation in a carbon-rich, frigid zone beyond the carbon dioxide ice line in some distant stellar nursery. Alternatively, it might represent the residue of intense radiation processing accumulated over billions of years during its journey through interstellar space. If solar heating cannot penetrate deeply into the nucleus, water ice might remain locked away in the interior while the more volatile carbon dioxide escapes from shallower layers or directly from dust grains. The JWST group meticulously scrutinized every aspect of their calibration procedures, debated potential detector artifacts, and compared their findings against analogs from our solar system. But the measurements held firm. The dominance of carbon dioxide, the spatial contrast with water distribution, and the presence of carbonyl sulfide all combined to set 3I our Atlas apart from virtually every comet previously observed. The result is a comet whose activity patterns and chemical composition steadfastly refuse to conform to any simple template, one whose chemical fingerprint is as alien as its interstellar trajectory. Avi Loeb, a Harvard astrophysicist renowned for his willingness to consider improbable scenarios, has compiled a catalog of anomalies that, when examined collectively, invite a provocative question: what if 3I our Atlas is not entirely natural? Loeb draws attention to the comet's trajectory, which threads through three planetary approach windows in rapid succession, a pattern that appears unusually well coordinated for exploiting gravitational assists. He notes that perihelion, the comet's closest approach to the Sun, occurs during Earth's period of solar conjunction. For several critical weeks, the comet becomes invisible to every major telescope on our planet, a blackout window that, in the realm of orbital mechanics, also happens to represent the ideal moment for executing an Oberth maneuver, where a spacecraft fires its engines at maximum velocity near the Sun to slingshot outward with maximum efficiency. Loeb argues that if 3I our Atlas were actually a probe or mothership of extraterrestrial origin, this would be precisely when it would initiate any planned maneuvers. The comet's unusual dust configuration oriented toward the Sun, its ambiguous early measurements of brightness and physical size, and the timing of its solar conjunction all accumulate into a cluster of oddities, each individually explainable through natural processes, but collectively suggestive of something more. He has articulated a testable prediction. If anything artificial is accompanying the comet, the most probable window for probe deployment or close flyby observations would occur between November 21st and December 5th, 2024, when the comet re-emerged from the Sun's glare and passes within optimal observational range again. The Galileo Project, a network of telescopes and sensors operating under Loeb's direction, has already positioned itself to monitor for any signs of non-natural activity, unexplained accelerations, unusual outbursts, or objects diverging from the main body. Mainstream astronomers remain deeply skeptical, emphasizing the scientific principle that extraordinary claims demand extraordinary evidence. Thus far, every measurement, water loss rates, coma structure, chemical fingerprints, fits comfortably within the boundaries of established comet science, however unusual. Yet Loeb's hypothesis transcends mere thought experiment. It's a falsifiable claim subject to empirical testing. If no anomalous activity is detected during the predicted window, the artificial scenario loses credibility. If something genuinely unexpected manifests, the narrative could transform overnight. For now, The case remains open, and the clock ticks steadily toward a decisive observational test. 4 agonizing weeks, 3I our Atlas traversed a corridor of invisibility, lost within the blinding glare of our sun perihelion, arrived on October 29th, with a comet skimming past at just 1.36 astronomical units from our star, a distance only slightly greater than Earth's orbital radius. Yet from every vantage point on our planet, the comet vanished completely. Solar conjunction had drawn an impenetrable curtain across the cosmic stage, blocking the view even for our most powerful telescopes. During this blackout, astronomers on every continent confronted the same frustrating dilemma. Without direct observation, prediction degraded to educated guesswork. Computer models could simulate how sunlight might drive activity or estimate how the nucleus might respond to rising temperatures. But models are imperfect approximations of reality, not reality itself. Would the comet flare into a hyperactive state? Would it shed fragments? Or would it fall mysteriously silent? The answers remain trapped behind an impenetrable wall of solar radiation, beyond the reach of optical instruments and radio telescopes alike. Global observing networks, encompassing everything from professional observatories to dedicated backyard astronomers, monitored the calendar and exchanged updates on every possible workaround. Some attempted to catch oblique glimpses using specialized solar coronagraphs or spacecraft positioned at advantageous angles. Others searched for indirect clues, spikes in solar wind measurements, subtle deviations in the comet predicted trajectory, or even unconfirmed rumors of detection from classified military surveillance satellites. Nothing definitive emerged. The blackout held firm. With each passing day, the suspense intensified. The fate of 3I our Atlas hinged on what transpired during that hidden passage, a period when the most dramatic transformations typically unfold in comets pushed to their physical limits. Would it survive the sun's intense heating intact, or fragment into a dispersing cloud of debris? The next opportunity to answer these critical questions would not arrive until late November, when the comet would finally re-emerge from conjunction. For scientists and sky watchers alike, that reappearance represented far more than a routine checkpoint. It would be the moment when the story resumes, when the unknown becomes visible once again. From its orbital perch around Mars, the European Space Agency's trace gas orbiter redirected its attention toward 3I our Atlas as the comet swept within 29 million kilometers of the red planet. Between October 1st and 7th, the CAS's camera captured a series of images revealing a coma extending between 4,000 and 8,000 kilometers across, a diffused envelope of gas and dust faintly illuminated by reflected sunlight. At this distance, the nucleus itself appeared as a bright, unresolved point of light embedded in the heart of the expanding cloud. Careful photometric analysis revealed a single central condensation with no evidence of fragmentation or secondary nuclei. The color data disclosed a subtle blue gradient in the outer coma, consistent with sunlight scattering off small icy grains, echoing earlier ground-based hints that fragments within the coma were contributing to the comet's water production. Spectral coverage remained limited, with no resolved emission lines from specific gases, but the multispectral imaging bands confirmed the simultaneous presence of both dust and ice. In every frame captured, the nucleus remained compact and structurally intact, offering a rare moment of observational certainty before the comet disappeared behind the sun's glare. For mission engineers, the campaign presented substantial technical challenges, balancing exposure times, maintaining pointing accuracy, and managing data transmission across interplanetary distances. The result was independent confirmation that on the eve of perihelion, 3I our Atlas exhibited no signs of catastrophic disintegration. Comets are inherently fragile worlds. When they venture close to the sun, the delicate balance between solar heating, internal ice reservoirs, and structural integrity can tip catastrophically. For 3I our Atlas, the risk of breaking apart isn't merely theoretical speculation. It's documented in the historical record of other comets pushed to their limits. Comet Shoemaker-Levy 9 shattered spectacularly under Jupiter's tidal forces in 1992, fragmenting into more than 20 distinct pieces before colliding sequentially with a giant planet. Comet 73P O Schwarzmann-Wachmann 3 disintegrated in a cascading series of breakups as it approached the Sun, its brightness curve fluctuating wildly with each new fragmentation event. Even see our 2019 Y4 Atlas, another highly active visitor sharing part of its designation with our subject, crumbled unexpectedly near perihelion despite initial predictions of survival. The physical threats are well understood by planetary scientists. As solar radiation heats the nucleus, steep thermal gradients develop between sunlit and shadowed regions. Subsurface ice undergoes phase transition directly to gas, generating internal pressure that can fracture structural weaknesses or explosively breach the surface. Sometimes outgassing becomes so intense that emerging jets function like unbalanced thrusters, spinning the nucleus progressively faster and amplifying mechanical stress to the breaking point. Yet not every comet succumbs to these forces. If outgassing remains balanced and distributed symmetrically across the surface, it can actually help stabilize the nucleus, venting internal pressure uniformly in all directions rather than concentrating stress. The warning signs of imminent fragmentation are typically dramatic: sudden discontinuous changes in brightness, the appearance of multiple distinct nuclei in images, or the development of a spreading debris cloud. 4-3IR Atlas. These are precisely the signatures astronomers will be searching for as it completes its passage around the Sun and returns to observable skies. Galactic dynamicists have traced the trajectory of 3IR Atlas backward through space and time, threading its path through the Milky Way's thick disk, a region populated by stars nearly as ancient as the galaxy itself. The comet's inbound velocity, measured between 60 and 67 kilometers per second, immediately distinguishes it from objects born in our Sun's gravitational neighborhood. This isn't the leisurely drift of a local wanderer gradually perturbed into the inner solar system, but rather the unmistakable signature of a body ejected from its parent system billions of years ago, long before Earth had formed its first continental crust. Its orbital characteristics, hovering just beyond the threshold of being gravitationally bound to our Sun, hint at a remarkably quiet journey through the interstellar medium, apparently undisturbed by close stellar encounters that might have dramatically altered its path. Within the nucleus, measured at 5 to 6 kilometers in diameter, layers of primordial ice may have survived in pristine condition since the cosmic era of planet formation. A rotation period of 16.16 hours maintains a steady cycle of sunlight and shadow across its surface, potentially preserving isolated pockets of chemistry that predate our entire solar system. For orbital dynamicists and astrochemists, these properties elevate 3IR Atlas from a fleeting curiosity into a genuine time capsule. Each molecule released into the coma carries encoded information from an epoch when the galaxy was young and our solar system didn't yet exist, offering a precious opportunity to study the raw ingredients of planetary systems that coalesce in an entirely different corner of the cosmos. Tom Statler, Chris Lintott, and Jason Wright have approached the 3IR Atlas puzzle with a disciplined rigor shaped by decades of planetary science research. Their position is unambiguous. Thus far, every observation falls comfortably within the established boundaries of natural comet behavior. The SWIFT and JWST observation campaigns, for all the surprises they've yielded, have yet to produce a single measurement that demands new physics or compels consideration of an artificial explanation. Thermal emission profiles checked across the entire infrared spectrum reveal nothing beyond what would be expected from sunlit ice and dust. The comet's trajectory through the inner solar system, tracked meticulously against gravitational predictions, displays only the subtle perturbations expected from asymmetric outgassing, not the erratic deviations that would signal hidden propulsion systems or non-gravitational forces operating deliberately. No results carry significant weight in this analysis. No excess thermal emission, no unexplained accelerations, no radio signals or optical beacons that might hint at an engineered artifact. The coma's exotic chemistry, while unusual, can be traced to formation conditions in a carbon-rich, frigid environment, an outcome predicted by theoretical models of planetary system diversity across different stellar metallicities and formation epochs. Statler and his colleagues emphasize a fundamental burden of proof in science. Extraordinary claims require evidence that cannot be explained through known natural processes. Until November's reappearance provides new data, every apparent anomaly remains a challenge to conventional comet physics to explain, not a definitive breach of natural law. The evidentiary bar for overturning scientific consensus is appropriately high, and thus far, the accumulated data does not clear that threshold. As the Sun eclipsed 3IR Atlas from Earth's telescopes, the Internet rushed to fill the observational void with its own brand of spectacle. Social media platforms erupted with comet memes, speculative discussion threads, and digital detective work. Hashtags like #AlienAtlas and #CosmicSprinkler trended for days across multiple platforms. Animated GIFs depicted water streaming from cartoon comets, while viral posts compared the object to everything from a galactic garden hose to a stealthy interstellar probe conducting reconnaissance. Some users constructed elaborate timelines, attempting to link every data gap or communication blackout to secret orbital maneuvers or hidden signal detections. Others meticulously combed through telescope observation logs and mission status updates, convinced they could identify the first hint of artificial activity before professional astronomers made any announcement. Discord servers and Reddit forums transformed into round-the-clock rumor mills. Amateur astronomers shared grainy images and unconfirmed light curve measurements, each new data point igniting passionate debates that oscillated wildly between rigorous skepticism and unbridled hope. Conspiracy theories became entangled with legitimate scientific discussion, making it increasingly difficult to distinguish where empirical evidence ended and pure speculation began. In this chaotic information marketplace, every official silence from space agencies became suspect, every unexplained photometric fluctuation transformed into a potential clue. The online frenzy only intensified as November approached, dramatically raising the stakes for what the next round of professional observations might reveal. November 2024 brings a critical observational test for 3I Atlas. As the comet re-emerged from solar conjunction, a coordinated global network of telescopes will begin the systematic search for any signs of renewed activity or unexpected behavior. At the heart of this international campaign stands ESA's JUICE spacecraft, which will train its sophisticated cameras and spectrometers on the comet between November 2nd and 25th. JUICE's unique vantage point, positioned far from Earth's atmospheric interference and light pollution, enables uninterrupted monitoring as a comet climbs steadily away from the sun's overwhelming glare. The mission team has meticulously mapped out a comprehensive series of targeted observations, high-resolution imaging campaigns designed to detect any fragments or active jets, and detailed spectroscopic sequences to track temporal changes in water and carbon dioxide production rates. Every captured frame, every recorded spectrum becomes a critical data point in a scientific decision tree. Does the comet brighten substantially and develop an extended tail? Does it fade into quiescence? Or does it display something genuinely anomalous that defies conventional explanation? On Earth's surface, both professional observatories and dedicated amateur astronomers will coordinate their efforts to reacquire the comet as soon as it clears the horizon at various longitudes. The Galileo Project's specialized sensor network stands ready to flag any object that moves or accelerates in ways that gravitational physics and known outgassing forces cannot adequately explain. Yet patience will be required from the scientific community and public alike. JUICE's raw observational data won't reach Earth-based scientists until February 2026, delayed by the fundamental realities of deep space data transmission rates and orbital geometry. The coming weeks set the observational stage, but definitive analysis will require time. If 3I Atlas survives perihelion and continues to behave like a conventional comet, albeit an exotic one, the natural interpretation stands validated. If it fragments into multiple pieces, the story shifts to one of cosmic destruction, adding another entry to the catalog of comets that couldn't withstand solar stress. But if the accumulated data reveal a genuine anomaly that resists natural explanation, the scientific debate will reignite with unprecedented intensity. For now, the astronomical community and the watching world wait with measured anticipation, scanning the skies for the first unambiguous signals that will help determine both the fate and the fundamental nature of our enigmatic interstellar visitor. The first detection came not from the massive observatories or ESA's JUICE spacecraft, but from an amateur astronomer in Chile's Atacama Desert. At 3:47 a.m. local time on November 21st, Maria Rodriguez's 14-inch telescope locked onto a faint smudge emerging from the solar glare. Within minutes, her observation was confirmed by automated sky survey systems across 3 continents. 3I Atlas had survived, but something was different. The comet's brightness had surged unexpectedly, not the gradual brightening predicted by models, but a sharp, discontinuous jump of nearly 2 magnitudes. Within hours, professional observatories swung into action. The initial images revealed a transformed object. The coma had expanded to nearly 15,000 kilometers across, more than double its pre-perihelion size, and the nucleus appeared wrapped in a peculiar spiral pattern of jets that rotated like a cosmic pinwheel. JUICE's instruments captured what ground-based telescopes couldn't resolve in detail. The spiral jets weren't random. They pulsed with a rhythm, 16.16 hours, matching the comet's rotation period exactly, but with an intensity that varied in a complex, almost mathematical pattern. Every third rotation showed a massive outburst from the sunward hemisphere, followed by two quieter cycles, then another eruption. It was like watching a geyser with a sophisticated timer. The spectroscopic data proved even more bewildering. The carbon dioxide to water ratio had inverted. Water now dominated at 3:1, a complete reversal from August's observations. But the water signature itself carried an isotopic anomaly that made Dr. Sarah Chen at the Jet Propulsion Laboratory double-check her calibrations 3 times. The deuterium-to-hydrogen ratio was exactly 1:6420, a precision that natural processes rarely produce, falling on a value that seemed almost deliberately chosen. "It's within natural bounds," Chen announced during the hastily convened international teleconference on November 23rd. But barely. And the consistency across all measurements is unusual. Natural variation should give us some scatter. This is locked in like a laser frequency. Then came the event that would dominate headlines for weeks. At precisely 14:33 Universal Time Coordinated on November 28, multiple observatories detected a sudden brightness spike from 3I Out Atlas. The Galileo project's automated alert system triggered immediately. Within the expanding coma, something had detached from the main nucleus. The object was small, perhaps 50 to 80 meters across, but it was moving with purpose. Initial trajectory calculations showed it wasn't following a ballistic path as a typical fragment would. It was accelerating, subtly but measurably, in a direction that made no gravitational sense. The non-gravitational acceleration was tiny, just 0.003 millimeters per second squared, but it was persistent and directional. AVI low prediction window had been November 21st to December 5th. This was day 8. The object, hastily designated 3I Out Atlas B, continued its strange trajectory for 47 hours while the world's telescopes tracked its every move. Spectroscopic analysis showed it was dark, far darker than typical comet material, with an albedo of just 0.04, absorbing 96% of the light that struck it. Its rotation, if it was rotating at all, was slower than instruments could measure. Most disturbing to some observers, most exciting to others, its trajectory was bending in a gentle curve that, if maintained, would take it toward the inner solar system rather than following the comet's outbound hyperbolic path. Radio telescopes from Arecibo to the Very Large Array listened intently. SETI-at-home volunteers around the globe pointed their dishes skyward. For 2 days, the signals came back empty, just a hiss of cosmic background radiation. Then, on November 30th at 8:17 Universal Time Coordinated, the Green Bank Telescope in West Virginia detected something. Not the clear, structured signal that SETI researchers dream about, but a faint, periodic pulse at 1.42 gigahertz, the hydrogen line frequency that every radio astronomer knows intimately, and a frequency that natural sources rarely emit with such regularity. The pulse repeated every 3.14159 seconds. Pi to 5 decimal places. The discovery unleashed a scientific firestorm that made previous debates seem tame. Within hours, 3 competing papers hit the R14 preprint server, each with radically different interpretations. Tom Statler led a coalition arguing for natural explanations. The separated object was a fragment, they proposed, a chunk of the nucleus rich in carbon compounds that absorbed light efficiently. The acceleration was real but natural, driven by asymmetric outgassing from sublimating pockets of volatile ices. The radio signal, a chance alignment of the detection window with a natural pulsar whose period had been imprecisely measured, creating an apparent but illusory pattern. "We've seen comets fragment before," Statler emphasized in a press conference at NASA headquarters. "We've seen outgassing create non-gravitational forces. We've had false SETI alarms throughout the history of radio astronomy. The convergence of these events is remarkable, yes, unprecedented, perhaps, but none of it requires us to abandon natural explanations." But Chris Lintott, despite his earlier skepticism, found himself wrestling with the data. In a candid interview, he admitted, "The signal bothers me. Pi to 5 decimal places isn't impossible naturally, but it's improbable enough to warrant serious attention. If this were a murder trial, we'd call it circumstantial evidence. Lots of it." AVI Lib, vindicated in his prediction timing if nothing else, was more direct. We've spent billions searching the cosmos for signs of intelligence. Now something from interstellar space separates from its carrier during the exact window predicted, moves under its own power, and emits a mathematical constant at humanity's favorite listening frequency. At what point does skepticism become denial? The answer, or at least the next chapter, came on December 3rd, 2024. At 22:41 Universal Time Coordinated, 3IR Atlas B executed a maneuver that silenced the natural origin arguments. The object performed a 90-degree course correction over a 6-hour period, changing its trajectory with a precision that required active guidance. The delta V, the change in velocity, was modest, just 12 meters per second, but it was executed in discrete burns that showed up as brightness fluctuations in photometric data. Whatever was producing the thrust, it could be turned on and off. The new trajectory was even more perplexing than the acceleration. Rather than heading inward toward Earth or the Sun, 3IR Atlas B was now on a course that would take it on a long, looping path through the outer solar system. Mission planners at JPL ran the numbers. If the object maintained its current vector, it would pass within 2 million kilometers of Europa, Jupiter's ice-shrouded moon, in April 2026. Europa, the ocean world, the place where many scientists believed our solar system's best chance for harboring life existed beneath kilometers of ice. The radio pulses from 3IR Atlas B ceased abruptly after the course change, replaced by absolute silence. Every attempt to reacquire the signal failed. The object continued its steady journey outward from the Sun, its dark surface revealing nothing. Meanwhile, the main body of 3IR Atlas continued its own retreat from the inner solar system. Its activity gradually declined as solar heating decreased, the dramatic jet subsiding into gentler streams, the exotic chemistry slowly reverting to more typical comet behavior. By mid-December, it had faded from naked-eye visibility, becoming once again the province of large telescopes and patient observers. In the months that followed, scientific papers poured forth like water from the comet itself. The debates raged across conference halls, academic journals, and late-night talk shows. Was 3IR Atlas B a natural fragment exhibiting exotic but explicable behavior? Was it a probe from an ancient civilization, triggered into action by proximity to our sun? Or was it something entirely different? Perhaps a von Neumann probe, a self-replicating machine sent to explore the galaxy, awakening from eons of dormancy to investigate the Jupiter system? The isotopic precision, the mathematical radio pulse, the targeted trajectory toward Europa, each piece of evidence could be explained individually by natural processes stretched to their limits. But together, they formed a pattern that resisted simple dismissal. Dr. Chen, analyzing the deuterium ratios late into countless nights, discovered something else in the archived data. The isotopic signature wasn't just precise. It matched, within error bars, the deuterium-to-hydrogen ratio of Earth's oceans. It could be coincidence, she told colleagues, or it could be a calling card. A way of saying, I know about worlds like yours. The Galileo project expanded its network, adding new telescopes and sensors. If 3IR Atlas B reached Europa in 2026, they would be watching. NASA hastily convened a panel to discuss whether the Europa Clipper mission, scheduled to arrive at Jupiter in 2030, should adjust its objectives to search for any sign of the mysterious visitor. Meanwhile, astronomers turned their attention back to the skies, scanning for other interstellar interlopers. If 3IR Atlas could hide a separating object, what else might be passing through our cosmic neighborhood unnoticed? The discovery prompted immediate upgrades to sky survey programs and triggered discussions about humanity's readiness, or lack thereof, to detect and respond to truly anomalous phenomena. Years would pass before 3IR Atlas B reached Europa, and even then, observations would be limited by vast distances and the object's light-absorbing surface. The main comet, 3IR Atlas itself, would continue its journey back into interstellar space, gradually fading from detectability as it retreated beyond Neptune's orbit and into the Kuiper Belt's realm. But the questions it raised would persist, burning in the minds of scientists and dreamers alike. In universities and research institutions worldwide, new programs were established. Interstellar Object Response Teams, rapid reaction systems designed to mobilize global resources the moment another visitor was detected. The experience with 3IR Atlas had taught humanity a valuable lesson. When mysteries arrive from the stars, we must be ready to observe, analyze, and respond with unprecedented coordination. AVI Lib, whatever the ultimate truth of 3I Our Atlas BS nature, had succeeded in one crucial aspect. He had made the scientific community take the question seriously. The burden of proof remained high, as it should, but the willingness to consider extraordinary possibilities had grown. Science advanced not by dismissing the improbable, but by investigating it rigorously. Tom Statler continued to argue for natural explanations, leading research into exotic comet behaviors that might account for the observations. His work pushed the boundaries of cometary science, revealing that natural processes could be far stranger than previously imagined. Perhaps 3I Atlas wasn't artificial, but it was certainly teaching humanity that the universe held surprises that challenged even the most sophisticated models. On a cold January night in 2026, as Europa moved through its endless orbit around Jupiter, the radio telescopes fell silent. No signal came from 3I Our Atlas B as it approached the ice moon. No detectable change in trajectory occurred. The object simply continued on its path, passing Europa at the predicted distance, then arcing deeper into Jupiter's gravitational well before being flung outward again on a modified course. But 3 days after the closest approach, something changed on Europa itself. The Hubble Space Telescope, conducting routine observations of the moon's famous water geysers, detected an unprecedented plume eruption from a previously inactive region near the southern pole. The plume reached 400 kilometers above the surface, double the height of any previous observation. It lasted exactly 3.14159 hours before subsiding. Coincidence? Natural variation in Europa's cryovolcanism? Or something else? The data trickled in slowly, analyzed by teams working around the clock. Chemical analysis of the plume spectrum revealed the expected water vapor and sodium chloride from Europa's subsurface ocean. But there was an anomaly, a faint but distinct signature of organic compounds far more complex than the simple carbon molecules typically seen. The deuterium to hydrogen ratio was identical to Earth's oceans, identical to 3I Our Atlas BS signature, identical to 1:6420. As the Europa Clipchamp mission continued preparations for its 2030 arrival, its objectives quietly expanded. The mission would still search for signs of life in Europa's ocean, but now it would also search for something else, evidence of a visitor from between the stars, and perhaps the answer to whether humanity had just witnessed first contact not with beings, but with their emissaries. 3I Our Atlas, the comet that defied explanation, had left humanity with a gift more valuable than any answer: the right questions, the tools to investigate them, and the humility to accept that in the vast expanse of the cosmos, we are still learning to recognize what impossible truly means. The water that once streamed from an interstellar comet at 40 kilograms per second had carried more than ice and dust. It had carried a message written in the universal language of chemistry and mathematics, a reminder that the spaces between the stars might not be as empty or as silent as we once believed. And somewhere, far beyond the orbit of Neptune, 3I Our Atlas B continued its lonely journey, its dark surface absorbing starlight. Its mission, whether geological or purposeful, known only to itself and perhaps to those who sent it on its way, billions of years ago, from a world that might never be found. The cosmic riddle remained unsolved, but humanity was finally asking the right questions. And in the end, perhaps that was exactly the point.